This is the second in a series of resources on limits. We consider the basic idea of a limit and provide a formal mathematical definition for a limit. We look at three instances where a limit does not exist. We explore various properties that make finding limits simpler and look at multiple examples. We consider what it means for a function to be continuous as it pertains to limits. We close the series by considering infinite limits. In the previous resource in this series, we explored the mathematical definition for a limit. We realized the general concept of a limit was to get progressively closer to the target x value and determine if the function was approaching a particular value. We also discussed the formal delta epsilon definition for what exactly it means to be approaching a particular function value. In this definition, L is the limit for the function at x value c if for any value epsilon we can find a value delta such that the distance between x and c being smaller than delta implies that f of x minus L is less than epsilon. So for a prescribed error allowance of epsilon, we can get close enough to x equals c to find a function value that is within epsilon of f of c. However, it turns out that these limits do not always exist. We will explore three different situations where the limit of a function does not exist. For a limit to exist, the function must close in on the same value when approached from the left or from the right. For example, suppose we consider the limit as x approaches 0 for the function f of x equal to the absolute value of x divided by x. We realize that for positive values of x, the function will equal 1. When x is negative, the absolute value of x divided by x will equal negative 1. Looking at the graph of the function, we have a horizontal line at positive 1 for positive x values, and a horizontal line at negative 1 for negative x values. But what does this mean for the limit as we approach 0? So the limit from the right, the positive side, is equal to positive 1. The limit from the left, the negative side, is negative 1. Because the function converges on different values from the left and the right, the limit as x approaches 0 of the absolute value of x divided by x does not exist. Another situation in which a limit does not exist is when the function is undefined at a value. This is usually the result of breaking the one unbreakable rule in mathematics: thou shalt not divide by 0. For example, consider the limit as x approaches 0 of 1 divided by the absolute value of x. The graph looks identical on both sides of the y-axis, but both branches grow without bound. Because there is no real number that both sides approach, the limit does not exist. One final form of a limit that does not exist is when the graph oscillates too rapidly to close in on a particular function value. Consider the limit as x approaches 0 of the cosine of 1 divided by x. Most of the graph of this function looks almost normal, but between -1 and 1, strange things happen. Let's look at some values to see what exactly is going on. Consider the x value of 1 over pi. When we plug this value into the function, we have the cosine of 1 over pi, or just the cosine of pi. This is -1. But what happens as we move in closer to x equals 0? If we have an x value of 1 over 2 pi, we are taking the cosine of 1 over 1 over 2 pi. This is the cosine of 2 pi, which equals positive 1. And when we get closer, if we plug in 1 over 3 pi, we have a function value of negative 1. And closer still, when we plug in 1 over 4 pi, the function is equal to positive 1 again. But what does this mean for our limit? Think about the formal definition of a limit. Because of the oscillation of the graph, no matter how small we choose our delta, we can find values x sub 1 and x sub 2 whose distance from 0 is less than delta, and where the function value for x sub 1 is 1, and the function value for x sub 2 is negative 1. Because the graph wiggles between 1 and negative 1 infinitely many times, we cannot find a single limit value, and the limit does not exist.